Okay, good evening. Welcome to
Calculus19.
So we have been talking about sequences in series last couple of weeks, but it was Thanksgiving, so we had a little bit of a break. So I'm going to start out. Sorry, that might not work super well. Start out with this series: 1 plus a half plus a third plus a fourth plus a fifth plus dot dot dot. This is known as the harmonic series.
Alright.
And what do you know about this series from the conversations we've had?
The series does not converge. It goes to infinity.
Alright. So what does that mean?
So
what does it mean when we say a series doesn't converge and it goes to infinity?
So it basically means that this series is greater than any n.
Okay. That at some point as we go along in the series there will be some term where the sum is bigger than any number n we pick. So that's interesting. I'd like you to give me two different proofs, or you don't have to be formal proofs, but two different ideas that show that this series diverges.
So just extend this out a bit. So I'm going to try to approximate this series, each term of the series with a value that's less than the term I'm approximating. And if I can show that that series diverges, we'll know that this series diverges. Because every term will be either greater than or equal to its corresponding term.
Okay.
So for 1, let's go to 1. For a half, I'll go to half. For a third, I'll go to 1/4. For a fourth, I'll go to 1/5, or 1/4, sorry. For a fifth, I'll go to 1/8. For a sixth, I'll go to 1/8. For a seventh, I'll go to 1/8, and for an eighth, I'll go to 1/8. So from this, and this continues, 1/9 to 1/16 will approximate as 1/16. So what happens here is you've got these groups between every power of 2 that add up to 1/2.
Okay.
So we can find we can find where this series is bigger than any number.
Okay, why? Why does your new series always get bigger than any number?
Because this is just equivalent to 1 plus 1/2 plus 1/2 plus 1/2 plus dot 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 dot.
Okay. Nice. And this is bigger than this series. So that means that series has to diverge. Okay, good. That's one nice way of looking at it. Give me a second proof that this series diverges.
Well, we can use the method, our integral test method.
Okay.
So this series can be represented as sum from n equals 1 to infinity of 1 over n, which we can use our integral test, which is going to say integral from 1 to infinity of 1 over x dx, which we know is ln x evaluated 1 to infinity, which is infinity minus 0. Or, no. ln of 1, yeah, ln of 1 is 0.
Okay.
In any case, this is infinity.
Yes. Okay. We're being a little bit loose here. We actually would need to write this as limits, but fine. So this is infinity. Okay, good. I'm going to give you a couple more series and see if you can make sense of them.
Okay.